Okay, so we are very happy to have Professor Nils Napp. I remember I met him the first time in Hong Kong, next to a huge statue of the Buddha. That was, I don't know if that was the first time, but I remember that. And he's been working in robotics and I would say like unconventional robotics, bio-inspired robotics. He recently moved to Cornell, right? So that's a new affiliation for him. And so today we talk about the abstraction barriers for physical embodied algorithms. Thank you, Nils.
Yeah, well, thank you for the introduction. So we're going to talk about sort of a few different research projects that I've done over the years. And I think like the way I want to think about robots as physically embodied algorithms. I might get to the rock stacking stuff in the end with that is a collaboration with Martin to some degree. But if we run out of time, I might sort of shortchange that, and we can do that during a question answer session offline. So just make sure. You can see this. Yes. Okay. So this is if you talk about algorithms and algorithm design in computer science. This is sort of one of the standard textbooks. These both happen to be Cornell professors, Kleinberg and Tardos. And I asked them why they picked this particular photo. I mean, it's a beautiful photo. We know why they picked it, just visually. But the explanation was that these birds, these are weaver birds, and that they're building a nest. And they thought, in addition to being a beautiful picture, that the algorithm that they execute is fairly well understood. So these birds, they take grasses and they build a nest. And the weaving is sort of, going over under to put these grasses together. The problem is that is actually it's not really known what these birds do, but you can imagine weaving, and there are some projects on robotic weaving to say that, oh, if you want to make a stably woven structure, then we need to do some sort of interlocking between grasses. Now, if you look at the sort of nest building behavior of birds, which is a pretty well-studied area, there are a lot of open questions, but there are lots of biologists who have watched birds build nests. Then the sort of younger birds, the first year after they try to build nests, are completely unable to successfully complete one of these nests. Like they start weaving, they try to tie a grass to one of these branches, and then they build for a few hours and the whole thing falls down. So what they do is actually very complicated. Right? And there are a lot of sort of intricate physical details that we don't really know if they would need to be modeled if we wanted to have some sort of algorithmic explanation for why it works. So for example, right, like, is it really just the sort of nodding interleaving of grasses? Or if we wanted to model this, do we need to model the bending behavior of the bending behavior of an individual grass when it breaks, when it buckles? Does it matter if you sort of model the surface friction by trying to figure out if there are little hairs on grasses, which sometimes is the case. So the reason that I think this is a sort of a interesting picture to look at is that it's totally unclear that if we want to describe this sort of on a high algorithmic level, what these birds do, what the necessary level of physical detail would be that we would need to take into account in order to accurately model this process. So the reason why I think robots are really fascinating is that if you think of robots as just these, there's lots of research on like the mechanical building, but if we think of robots as just these programmable machines, then the robots, we program them, they do some sort of work in the environment. And before and after a robot program runs, the world has a different state. And this is similar to computation, where we can write these programs, and before and after the program runs, there is a different sort of 0-1 representation somewhere in memory in one of these is somewhere in memory for a general purpose computer. So I want to try to figure out if we can think of robots as embodied algorithms, where we think of the work they do on the environment and the sort of how the state before and after a robot runs changes. So that means that if we wanted to do this, we need good abstractions for how robots interact with space. I'm going to talk about some of the work on sort of the real world use cases for this, which is robotic construction, and sort of what the technological drivers are that we can exploit in order to make this happen. So I want to think of the programmability of robots as embodied algorithms. So the use case of construction, where we basically care about what the robot builds, I think is a compelling area for trying to figure out whether or not this is something that needs more automation or needs more robots. So the construction industry is changing pretty quickly. And there are a bunch of external drivers to this. One is that there's a huge demographic shift of where people choose to live, which means we need to figure out how to quickly build houses and how to quickly build infrastructure. And robotics would be one way of doing that. There's a lot of growth expected all over the world, where in order to build sufficient housing for people, we just need construction to be more efficient and cheaper, and robotics are also a way of doing that. And climate change, man-made disasters for displacement also mean that people move, and there are a lot of refugees in the world that need access to adequate housing. So all of these sort of mean that we need better technological ways of quickly building things. So I'm going to go through a few things that I've worked on in my group, and you can loosely organize them by how the environment is represented. So some of the abstractions that you use if you represent external space are using a sort of discrete representations, where I think of whether or not the state of the world as sort of this discrete occupancy grid. And that's the abstract representation. This shows up in real world scenarios, for example, for bricklaying robots. Then I've worked a little bit on how to have robots interact with much more irregular space, irregular obstacles or irregular environments. So that means that the building material needs to be different, the representation of the world needs to be different, and the algorithms need to be different. Then the last thing that I wanted to mention, if we have time, is to talk about ongoing work on trying to use found objects to build structures. Building with discrete, rigid building elements has been around for a long time. This is by no means an exhaustive list, but it goes back to sort of modular robots, then modular robots trying to put together rigid building materials, then several sort of quadcopter flying things, and then a lot of sort of swarm building and group coordinated group building behaviors are normally explored using rigid building elements. So this is so that's on the research side. Sorry, let me see if I can turn this down. And this is a company in upstate New York. So it's a few hours from us, called Construction Robotics. There are a number of companies around the world that are trying to automate bricklaying. This is just one of them. They are reasonably successful. So this is a robot that is deployed all over the US, mostly sort of in the like sort of down the Atlantic coast and then further down south, just because like sort of union and labor costs differ widely throughout the United States, and whether or not it makes sense to have this robot really depends on sort of the construction logistics around around this machine. So the way this works is they have this pretty nice display where a designer, or pipeline where a designer just designs sort of a brick facade. They get to place bricks, use different colored bricks. That then goes to some sort of construction planner, and it's shown on the right, top right. It's a little hard to read, but basically every brick has a number, right? So this goes from 1 to several thousand or tens of thousands for a normal facade. And it's entirely predictable what the robot needs to do. And then the robot just goes through and basically executes this plan open loop. This is pretty similar sort of from a representation point of view for what some of these research construction sort of robotics researchy construction type systems look like. So this is work we've done, I've done in collaboration with Professor Peterson, who built the Hermes robots. And there the question is similar to the planner that is used by construction robotics. What is the order in which these robots should put together discrete building elements? So there the questions are slightly different. Where in the Hermes type robots, you normally try to figure out how I can have groups of robots put together large structures. And there I want to figure out how to maximize parallel execution. I want to figure out how robots with minimal communication and minimal sensing can reliably build these large structures. We worked on a compiler that spits out, you give it the structure you want to build. The compiler knows all the physical constraints between building elements, and then gives you some sort of order or a partial order in which these bricks can be put together. And the order is such that it is locally checkable by individual robots. We worked on kind of speeding up the original compiler by like orders of magnitude by turning this into a CSP, and then first a CSP, a constraint satisfaction problem that scales a little bit better, and then having a compiler that basically is a constructive approach to come up with relatively large plans quickly. So the abstract problem on having rigid things that have assembly order constraints is really similar between sort of this commercial system and the Hermes compiler, where here are two different plans. It has the same number of discrete elements that are being put together, and the one on the left is similar to what the construction robotics system does right now. It's basically a total order where there's one pathway through this type of assembly. And the one on the right is more like what we worked on with the Hermes system, where we're trying to figure out all sort of the different pairwise constraints that are locally checkable. Where, for example, if I wanted to put down, I don't know if you can see this, if I wanted to put down the brick in location number 8, then all I would need to check is that 2 and 9 are there. And I can figure out whether or not this is a legal assembly move by just checking the local environment. Now, the reason that you would care about sort of this parallel execution in practice is that on a construction site, normally these different fabrication steps for a building don't happen in isolation. And often there are sort of exclusion areas that pop up randomly. For example, if there's an overhead crane or some other process that temporarily blocks some region of a construction site for safety purposes. Then right now, for example, if region number 6 or location number 6 was blocked, it would mean that all of these, the robot would just have to wait, right? Because the only thing that can happen after 6 is that brick number 7 gets assembled. So basically, this robot is forced to wait. Here, if if brick number 6 is, location number 6 is blocked, then the area that is actually sort of illegal to move to is much smaller because this representation of precedence constraints actually allows a lot of other things to happen, sort of different ways of assembling this structure. So if you are currently at location number 4, location number 6 is blocked, then here you could only do one move. And here, if location number 6 is blocked, then if number 6 is blocked, then so there's sort of a difference in these representations where the green area are the things that you're still allowed to do, or the difference of the things that you're still allowed to do between the system. The reason that I'm looking at this is that I want to find out from a programming perspective, sort of how the physical assembly order constraints and the program that the robots execute are linked. To do that, we look at partial orders. I know that a lot of you have worked with partial orders that are continuous, so just go over it very quickly. So partial order is a set that's reflexive, and a set and a relation that's reflexive, antisymmetric, and transitive. So it's very similar to a normal order, but not all elements of the set are relatable. So for example, the subset relation is a common example for partial order. For assembly sites, an example would be 9 and 2 are not relatable because they both need to happen after 1, but it doesn't really matter in which number, in which order number 2 and 9 happen. Here's a sort of toy example of the Termi system that we're going to think about as a partial order and try to figure out whether or not the sort of restrictions of how I assemble it and how I program this assembly, how they match with the sort of the programming matches the physical constraints of the robot. So the physical constraints are that that are both true for this Termi system and for most sort of brick-laying robots, is that it's impossible for me to insert a brick into a location that has bricks that are constrained on both sides. And that the assembly normally needs to stay connected. I can't normally sort of start from 2 really different locations that are far apart and start the assembly and then hope to have them merge just because of the way that errors accumulate. Given these 2 constraints, there are only so many ways that I could put together this example system where I'm trying to build the simple 9x9 square. It's a discrete occupancy grid, and I'm trying to figure out whether in which order I'm allowed to put these discrete building elements. So this is a sort of a partial assembly state. So right now, I don't know if you can see this well, but some of these things are in white, some of them are grayed out. So right now, locations 0, 0, 1, 0, 2, 0, and 1, 1 are occupied, and the grayed out ones are not occupied. And this corresponds to a partial assembly state that is shown in this partial order right here. So here they have X's for the locations that are occupied and zeros for the locations that are not occupied. So this picture in the middle is a partial order, it has size 28, and it is all the intermediate states that you can reach if you take into account these physical restrictions of assemblies not being allowed to put in between sort of this assembly order constraint that I'm not allowed to put a brick into a location where the 2 neighbors are already assembled, or 2 opposite neighbors are already assembled and staying connected. So if I wanted to enumerate all possible states for something that is larger than just 9 locations, this gets intractable very quickly. Basically, I have a combinatorial state-space explosion, so it's really hard to reason about sort of all the partial assembly states in a large house made of bricks using this assembly, using these assembly constraints. So something that we're currently working on is trying to sort of understand the restrictions that we get from this distributed Termes assembler, and where there are some states that are physically possible. If I was sort of you know, if I as a person was just taking into account the physical constraints and try to reach, sort of look at all the states I can get to, that is a strict superset of the states I can get to using a distributed assembly algorithm that requires that I have locally checkable rules whether or not I'm allowed to make an assembly, take an assembly action. So the assembly rules are shown here on the bottom left. The rules that our compiler spits out for the Termi system look also like a partial order, right? It look like a partial order where I'm saying 0, 0 is the thing, is the start, it needs to be assembled first. After that, 0, 1 or 1, 0 could be assembled. And the assembly rules that a robot that a robot executes is it checks whether or not its precursors are there. And if they're both there, then I'm allowed to assemble this. So what a robot needs to now do is, for example, at location 1, 2, it checks whether or not 0, 2, and 1, 1 are assembled. And if they're both there, 1, 2 is, it is allowed to assemble 1, 2. Now these arrows, they are only between neighbors, which means that a robot is able to sort of locally decide whether or not it's a legal move without getting into these deadlock situations where if a robot, for example, tried to start here in 0, 1, and another robot started at 1, 2, I would get into the situation where I am no longer able to assemble 1, 1. But the problem is that these two are not neighbors, so I cannot really directly check whether or not an assembly move would result in deadlock if I go from, if I sort of start from arbitrary states. So now if we think of this as a partial order, there are a lot of partial order tools out there. So we can compute what is called the order ideal, or I, for this partial order. And an order ideal is basically the set of all sets that are closed under the relation, so, or downward closed. So for example, so for each element in the set, all the elements that are smaller in the partial order also need to be in the set. So that gives a really natural correspondence to assembly states that it could have reached using this partial order assembly plan. Now, here is a picture of the order ideal from this assembly partial order. And you can see that some states are missing, and there are some choices that are sort of made by the compiler right now to only assemble the structure, to sort of give some hard constraints on how the possible pathways in which this thing can be assembled. Now, the nice thing about the order ideal is that its size, there's some pretty efficient iterative ways in which you can compute that without having to enumerate all the states. So now I can say, all right, here's this distributed assembly algorithm that I can express as a partial order. I can now compute the number of possible states that it could reach using this, this partial order assembly plan. And I can try to compare this to the number of possible states that are physically reachable, right? So this is a way for us to now say, so this plot on the bottom is the number of components. On the top is the number of possible states that you can reach. Just for comparison, I put down this dotted line, which is basically the number of states you can reach if there are no physical constraints between bricks. If I take each discrete building element and just say whether it's there or not, then I have 2 to the n combinations, so just the combinatorial choices of occupancy. And obviously, that's not true, right? There are a lot of physical states that would require bricks to fly that are totally unreasonable that I can never reach. So now I'm comparing the size of the order ideal for my assembly plan to the number of states that are physically reachable, where I don't take into account the programming constraints, but only the physical constraints for this particular sort of building system. And these are actually pretty close, right? So the order ideal of the action partial assembly plan expresses partial order, and the number of physically possible states, one is strictly smaller than the other one, but if compared to both the single building plan, where I just have a sequential total order of actions, like is being used in industry right now, or the no constraints, then sort of the distributed building plan and the number of possible states that I could reach if I had like all the knowledge are pretty closely related. So we think that for the Termi system, at least, that the sort of programming and the physical constraints put in by the building material are fairly well matched. So if we think about embodied algorithms, then there are certain things that discrete building elements allow us to do, right? So we can take, you know, in theory, you can take sort of any thing that has discrete elements, figure out what the constraints are for the assembly order. Then we can build this like pretty general purpose compiler, either by solving a CSP or constructively having building plans that now give you a partial order of assembly states. And we can reason about sort of if I want to have a parallel execution of this program, sort of how does that relate to the physical constraints of the system. I can reason about blocking for real world applications where I can say, well, this thing that we used for a parallel assembly in research actually now gives you these plans that are much more flexible if I even have a single robot. And we can now have sort of measure how well a programming, how the programming of a system is matched to the physical constraints of a you know, some kind of discrete assembly task. I'm happy to answer. I skipped a bunch of details. I'm happy to answer later, but sort of I want to move on to the next type of abstraction that we use, where I want to use more complicated building materials as a way to allow us to build structures in more complicated settings. So if I think about both the bricklaying robot and sort of this Termes type of you know, multi-robot assembly system, then it's very hard to imagine how I would apply any of those insights or systems that I build directly to a setting like this, which is a disaster site after an earthquake. Right? And really, this is where we want robots to go. Right? We want them to do stuff that is dangerous. We want them to operate in environments that we either can't go to or don't want to go to. So we looked at a bunch of different biological systems that do construction. This is from a review paper where we looked at some of the sort of commonly studied biological construction systems and looked at the number of agents in this construction system and the size of the structure they built, normalized by their body size. And you know, like animal construction is awesome. They are able to build huge structures using very decentralized methods that are very robust over many orders of magnitude. They don't really have a blueprint. They're able to use mostly materials that they find, especially in the context of sort of beavers and these leafcutter ants, where you know, the parts they work with are really irregularly shaped, and they're able to build these structures very reliably, and also adapt the structures to sort of damage. And you know, if a beaver dam is halfway done and you start putting a bunch of rocks down, it will just sort of adapt and deform around it. So the reason that we think this happens is that we have adaptive behavior, basically, right? So this is a picture of termites. This is a sort of close-up picture of a termite manipulating a dollop of mud. On the right are two pictures of termite mounds in the same part of Africa. These mounds are probably less than a mile apart, same species. One is freestanding, one is built around a tree. So and presumably the termites do the same thing. Right, so the reason, so somehow they are encoding their building actions in such a way that the outcomes, the physical structures in the end could look totally different, but presumably they're both functional based on the requirements of the termites. So we think that there are a few reasons for that. One is that it's basically all animals we think have this reactive building behavior where they don't have a blueprint and then just sort of open loop execute it. Instead, they go through and sort of repeatedly interact with the environment. And because they get to observe what the outcome of a previous action is, that somehow gives them a way to adapt, their building. We also think that the goal of animal construction is encoded by function as opposed to a specific shape often. So that allows a termite or some other animal to look at the partially built structure, figure out whether or not like it's already working or not working. And if it's not working, modify it modify it so it is closer to working. And then lastly, and this is related to how external space and building materials are represented, at least in the case of termites, I don't think this termite building or the mound on the right would be possible if all the termites had to build with would be sort of little Lego bricks that are discrete in size and rigid. So somehow this combination allows these termites to build the mound. And we're trying to come up with a sort of abstract representation of this that allows us to design algorithms for robots that have some of these same properties so that they can interface with really irregular environments, that we can make reactive building algorithms that are robust to disturbances. So we tried to look at a very specific example of this to first start wrapping our head around this. We call this like the ramp building problem, where I have multiple robots, they have limited sensing, their behaviors are reactive, and I want to let them go into an environment where they modify the environment repeatedly, and then once they're done, there is a ramp that is navigable both for them and maybe other robots and people. So I'm going to talk really briefly about sort of the three elements that we need to design these algorithms. One is how to model the external world, then how to model the goal, which is to build a ramp in an abstract way, and then how to model depositions that allow you to use deformable materials and do all of that in a way that is tractable and that we can design stuff around. So because we want to work in really irregular terrain, I think sort of discrete blocks are out as a representation. So we are using continuous height functions where the state of the world is described as this non-negative function over some compact building domain. The robots, they interact with this domain, they drive around, they make modifications. And then afterwards, I have a new height function, h1. So this is a continuous in space and discrete in time, where I think of the operations on the space as happening during discrete building episodes. We need now, if this is the goal of the robot, if we can make these types of modifications, then we need a way of describing whether or not the ramp is done. We played around with a lot of different ways of doing that. One of them, the thing that we ended up doing is that for a ramp, basically, you want to limit the slope, which for continuous functions would be Lipschitz continuity, where I take any 2 points and then the slope between those 2 points is bounded. That ends up being almost right, but way too restrictive if we want to map this to a physical system. Because if I have a robot with like a wheel that is like 10 centimeters high or 20 centimeters high, then even if there was a discontinuity of like 1 or 2 centimeters in there, it would not be Lipschitz continuous because there'd be a little step, but it's something that is totally irrelevant to the motion capability of the robot. So we added this little thing, this little epsilon that says that I need to be close to being Lipschitz. And then once you do that, you also need to say that this is a local property, because if I just allow these little steps, then I need to prevent that little steps sort of add up right next to each other and then again make a obstacle that a robot can't drive over. So we're saying something is almost locally Lipschitz continuous, then it is navigable. So this is a pretty abstract definition, but I think the way to think of this is to say, well, you give me a robot platform, and now I can give you these parameters, and maybe they're a little conservative and they don't capture everything about the kinematics of this robot, but I can pick them conservatively so that if the structure is navigable by this definition, then it is certainly something that the robot can drive over. So the last piece is modeling amorphous depositions. So the way that we're going to model depositions is that we're saying there is a shape function that is parameterized by some set of parameters. Here it's an upside down cone, and what the robot is allowed to do is it chooses the parameters of this function. Here it's the location and the height of this upside down cone. Now I can put this all together and say I have a deposition operator that takes one of these deposition functions, my current state of the world n, hn, and then produces the new a new height function hn plus 1, and then I take the max of both of those things, and that's my new state of the world. So this is h1. So now I've taken this problem of like ramp building in a super unstructured environment into this like pretty abstract, very concrete mathematical question to ask, like, is there an algorithm that if I do sort of repeated application of D to this space, what are the properties of the fixed points? Will this ever stop? What are the possible outcomes of height functions after I do this over and over again? So we developed like a series of algorithms for ramp building. In the 1D case, you can show that, you know, if you basically go forward until you find a non-navigable obstacle, then deposit one of these things, possibly with noise, then this process will stop and eventually build a ramp that is navigable by these definitions. So this is a pretty high level MATLAB simulation of this process, but basically this robot tries to make progress until it no longer can and then deposits. The depositions here, sorry, I forgot to mention this. The depositions are such that this algorithm will work as long as the deposition the robots make are bound by this shape function. So it doesn't need to be a precise modification of the environment. As long as I have some idea of what the robot does, is sort of bounded by this shape function. Here, there's a little bit of additive noise to the shape function. The reason that we picked that is that at the time we used sort of polyurethane foam that was slowly being drizzled out. This, if you take a cross section, actually looks a lot like a cone. So it was sort of a natural way of parameterizing that. Now, this is you know, works in math, but we sort of added enough, we think we added enough sort of parameters or the uncertainty in the system to now use this as a template to design actual robots. Specifically, on a very high level, we're now able to trade off the motion capability of a robot to say if a robot can drive over much rougher terrain, to its building material or like sort of building capability, to say that a robot, if it is, you know, can drive over really big obstacles, then its building material doesn't really need to be super fine. We don't need to make smooth surfaces. So we're able to use larger building elements or sort of more noisy processes. And we can also directly relate this sensing uncertainty to say we need to be able to resolve what the environment looks like to within some epsilon, so that even if there is no sensing noise, even if there is deposition noise, the robot with a specific motion capability is able to drive over this object, or over the ramp that it's building. So in the last few years, we've been looking at various building materials and platforms to make this happen. I just want to quickly point out that like these definitions of Lipschitz continuity, they're first presented in 1D, but the whole thing just works in arbitrary dimensions. So instead of having a slope, I have these cones that I check locally to see whether or not 2 points are navigable by the robot definition. So here, all of these obstacles that are over this cone would represent obstacles that the robot cannot drive over at that point. We looked at various building materials. So on the right, you can see a foam that I used in the original version of this work. We've also looked at complying building compliant building materials where the robot plans with these cones and then use the cone to decide whether or not it can put down one of these sort of compliant bags, where I think these are either pebbles or small balls that we ended up using. On the lower right, you can see one of these deposition function or shape functions that the robot uses, and sort of the superposition of several hundred bags that are being deposited. So we can match, even if we use these bags, we can reuse the same deposition function because we have a robot that is able to relatively reliably put stuff under these shapes. So the building process, so this is from a paper a couple years ago with 2 of my graduate students and an undergraduate, Walker Gosrick. And here, basically, we now do this same thing that we did in 1D super abstract, where we now have this robot. It drives around, it repeatedly interacts with the environment to try to build a ramp over this very unstructured terrain using compliant building materials. And there are a lot more subtleties by turning this into, like, there are a lot of sort of things that can go wrong by turning this from this like high level 1D representation into a 2D problem. Most sort of mathematically, the thing that's really different are not so much the depositions, but the path planning, where to get the correctness proof for ramp building, I basically need to cut up the world into regions that are navigable and regions that are non-navigable. And then I iteratively go through at the boundary, right? And then turn non-navigable features into navigable ones. And I sort of iteratively shrink and grow that area. In 1D, right, like there's only one way in which you can go. Like there's a point and it just moves back and forth. In 2D, I have these areas here shown in yellow for non-navigable and blue for navigable. And I need to reason about all the sort of like whether or not that space stays connected. I need to do path planning in that space in order to actually execute this high level algorithm. So that's something we're currently working on. We, in this first pass at the system, used not a very sophisticated motion planner and just, kind of went with easy implementations for all the different pieces. So this is a video. Let's see if this plays. This runs over several hours. And right now, the students are not allowed to go into the blue box. So everything inside the blue box is totally autonomous. All the planning of where the bags go is done by the system. The robots right now, to make it easier for the robot to actually pick up bags, we feed it new bags. And if it runs out of power, it drives outside of the square and we change the batteries. So this works pretty reliably. It works pretty reliably because the sort of steepness of the ramp the robot is trying to build and the deformability of the bags, they're kind of matched. It's pretty easy to come up with parameters where, like, the thing is really steep and the bags are not actually sort of strong enough or rigid enough to support some kind of very steep ramp. But if you're staying within these sort of relatively shallow things, then this algorithm works very well. And it's reactive in the sense that if you go through and have a graduate student sort of like kick the whole structure, once it's halfway done, the robot will just go back and fix it. And then eventually it will try to reach a goal location. Because the deposition, the model that we use for deposition is has so much uncertainty in it. It's also very easy for us to use different building materials and sort of see if you can get an advantage from building with larger rigid elements that take up more volume and bags. And combining that actually makes the whole process much more efficient, mostly because most of the time the robot spends driving around and picking up stuff. So if one deposition can take up a lot more volume, then there are a fewer number of steps that you need. So we build a system that has sort of fine bags to make a better ramp, coarse bags to be compliant, and then large rigid building blocks for taking up volume. It's the same high level algorithm. And as long as you can kind of figure out like some shape function that these depositions stay under, it works. Now there's a lot more physics that gets abstracted away. So we try to build this with all blocks, and it doesn't really work because they're too slippery. So even, you know, in a representation, I have these height functions, they're sort of assumed to be rigid. And if the building material that you use does not really fit that sort of implicit hypothesis in the of the algorithm, then obviously it doesn't work. But if I mix the two and sort of mix bags that are compliant and sort of provide friction between these rigid building elements, then I get a process that works much faster and works very well, right? And because I make very few assumptions on like what the actual robots look like, they can all have different capabilities, they can all have different end effectors, and it's easy for me to you know, sort of synthesize them based on the requirements of the sensing and the building and their motion capability. So currently we're trying to figure out like sort of what the deformation means or how to capture that in this more abstract way. So here on the left, you can see the sort of shaded areas or deformations in the bags as the robot is like repeatedly interacting with the structure. So as it drives over, all the bags deform. So we mapped out during building where the bags deform most and how much they deform. And I think if we really wanted to turn this into a more functional system that is easier to generalize, then that's something that we need to figure out, sort of how to model the stability of the structure, the expected stability and the expected failure modes. Running a little short on time, so I'm going to give like the high level version of this and then answer questions. So the last thing, so with building with bags works really well, but I don't really want to send like a robot into some really remote environment having to bring all the sandbags that it's going to use to build. So we want to figure out whether or not we can use found materials, rearrange them, and build structures reliably. And the idea is trying to figure out how to do dry stacking with found rocks and see if we can sort of come up with high level planning primitives that would allow us to then actually sort of on a more abstract level, say we want to build this large structure using dry stacking and then come up with plans that you can execute. In order to do this reliably, we first looked at the literature for dry stacking. So this is from a book about walls around the world. Depending on where you are in the world, walls look really different. That depends largely, like we think this depends largely on the building elements that you can find, that they somehow get reflected in the structures that you can build. So we looked at some sort of historical data from pictures of rock walls and tried to come up with like try to figure out if there's some way in which we can describe the statistical distribution of the shape or just, you know, approximate it. So the things that we looked at is like sort of how close to rectangular something is, because it's really close to rectangular, then, you know, you back to brick stacking. Looked at the distribution of sizes within a building. And then also the aspect ratio, because that gives you some sort of, if I have large flat areas, I can actually build stuff stably that way. So if I look at different rock walls and map these different shape parameters and just sort of do a scatter plot, then those distributions are actually, they overlap, obviously, but they look pretty different. So what we want to do is try to figure out if we can say, we can build a system where I give you a pile of physical rocks. I come up with a shape distribution. Now I generate my plans based on the shape distribution to figure out that if I now go to a new area where I know something about the statistics of what I'm expected to find, then I have a certain probability of success for building a particular shape. And then we want to figure out how to take these sort of now geometric shapes that become targets for lower level plans on stacking and how we can put them together into sort of large area building plans. Now, it's pretty reasonable to expect that even if I send a robot into a totally new environment, that I know something about the statistics. So if I look at sort of surveys of geology for rock walls in England, which there's a lot of there's a lot of rock wall pride in England. So there's a pretty good body of literature and databases on rock walls. But if I go into different geological areas, I should be able to expect certain types of rocks based on how they were eroded or weathered. I should know something about their shape. And, you know, if I want to do this on sort of extraterrestrial settings, there, you know, a lot of the early reconnaissance mission for going to new planets or moons normally sort of quantify and classify the regolith and rock size distribution. So when I go somewhere new, I can try to figure out whether or not I have, I can assume that I have some way of getting some idea of what I will be able to find. So I'm going to skip over this, but this is a work that I am working with Marco Hutter and Martin on trying to figure out how to come up with basically dry stacking plans. We have a few different, we tried a bunch of different stuff. We tried different heuristics. We tried Q-learning to solve this problem because it's a pretty messy problem. But basically, we're trying to figure out anything we can do to come up with like some way for robots to build dry stack walls reliably. Right now, we're using like pre-scanned rocks. I think this is a model. This is one that was built by one of our robot arms in an experiment. And we're just trying to figure out like whatever we can do to make these make this dry stacking work. Our goal, as I said, is then trying to come up with composable primitives, where then we can synthesize high-level plans using these composable geometric primitives and then execute them with dry stacking. I think on the dry stacking work, there are a lot of interesting questions for trying to figure out what the primitives should look like. Obviously, sort of blocks that look like bricks would be easy for planning because there are a lot of tools for that. But based on the rock walls that we can find, it's feasible maybe to find other distributions and other shapes that would be easier to build stable rock walls with. So just to wrap things up, I looked at it. In our group, we look at a few different ways of representing the environment in order to synthesize high-level plans, right? And our goal is to build robot systems and algorithms that allow us to change the world in predictable ways, where from an algorithm design perspective, I want to figure out sort of what an abstraction barrier is that I can use to then synthesize plans that I can then reliably execute with robots. And I have hopefully a few minutes for questions. Otherwise, thank you for your attention.
Thank you, Nils.
Yeah, thank you.
Thank you. Question, so are you allowed to like survey what are all the pieces and then kind of like make a plan to ordering them, right? Because, you know, sometimes, you know, I never built a rock wall, right? But,
yeah.
But I imagine that you kind of, you know, put the pieces together and maybe try to make a little bit of a plan of how you imagine them to fit, right? So
yeah. So right now, I think most methods that we know that we actually use to build use pre-scanned rocks from a relatively small library, like on the robotic side. We've played with sort of getting a stream from a shape distribution in simulation, where I just look at a rock and say yay, nay. I try to fit it. I get to throw it away. I don't have to use it. If you look at the literature, so it's interesting because this has, you know, like people have built rocks for hundreds or thousands of years. There's a fair amount of literature for this sort of skilled craft of rock wall building. And step one is normally look at all the rocks you have, take out the really ugly ones, get the big ones because they're good for corners, take the nice flat ones because those are the ones you use. So you certainly do some sort of triage. And
so I do have a possible future as a
yeah. No, it's exactly the right intuition. And you know, I talked a little bit about the shape distribution because I think if I really want reliable behavior, then I need some guarantee. Like I need some way of convincing the person who's buying this robot or NASA that I'm sending this robot to Mars. It's going to travel there for a year. And I don't want to be in a situation to say like, oh, you know, the rocks that I wanted to use, I couldn't really find them. So out of luck, right? So I don't know what the right answer is, but I think it's somewhere in between. I think like if you want to do sort of probabilistic guarantees to say, well, you know, if your rock distribution falls within this distribution, like I can guarantee you that we can probably build something if we're able to, and using 50% of the rocks on average, right? Because one sort of really lame way of solving this problem would be to look at all the rocks in the world and pick the ones that look exactly like bricks, and then say, "Ooh, I have a plan to work with arbitrary objects." But it means, you know, I only pick like a very narrow band of the distribution.
Right.
Yeah.
You cannot break rocks, or you cannot manipulate rocks to make them.
Realistically, yeah, probably that's somewhere down the road. I also think like dry stacking is pretty restrictive. It's super hard, right? So if we can do it, it'd be fantastic. But normally, like if I'm able to like even just put sand in there, or like put some small gravel on there, like it changes the contact geometry drastically. And what NASA cares about is the amount of weight you ship. So if I can tell you that, well, if you give me like just a tiny bit of glue or a tiny bit of cement, suddenly this whole structure is going to get much better, then maybe that's something that's worth doing, right? It's just
yeah, you know, what I had in mind is that, you know, maybe you have some like ugly shaped rocks, right? But you know, maybe you have a bunch of other smaller rocks that kind of can fill in the gaps. And I was actually looking at one of your slides, right? So
I think I saw one of these, right?
No, I think it's the one that was built by a robot arm or something. So you have a picture of a wall. No, this one. Yeah, something like that.
Yeah,
this picture here, right? So you see that you have a bunch of, you know, like holes and stuff, right? So you can imagine, what if you had some, you know, like a smaller rock, or, you know, if you had a hammer that you can, you know, hit one of these rocks so that you can make smaller rocks, so that you can put them in the holes, right? So, and you know, clearly, if you have some sand or some cement or some glue or something, you can do a better job.
Yeah, right? I think it's a very fair comment. I mean, I think if you for any realistic system, some of those things would need to be included. And I think the rock stacking literature, like, I mean, this is sort of a hard problem that we use sort of as a goal. I think we're also focusing on sort of single stack walls, which are much harder because they need to be sort of self-stable. Often people use they build actually two walls that are sort of slightly unstable against each other, and then, and then fill the middle actually with pebbles and sand. Then like the grass planning becomes much harder, because now I have this like area inside that, you know, somehow the robot arm needs to get into. But I think these are all like good things to do. Like, this is not done. I don't think this is quite ready for prime time. But I think, you know, we're trying to figure out like, you know, what are the things we can do to basically say, all right, we have this rock stacking capability. It can build you a structure that is, you know, X amount of strong with X amount of uncertainty.
Right. So because you mentioned before there was this streaming, right? So you get a rock, yes or no, right? You play Tetris, right?
Yeah. Yep.
In Tetris, you do have a preview. So you have the you know, the block that is falling, and then you have a preview of what is coming next.
Yeah.
Right. So what if the streaming is actually, you can take a look at the next 5, you know, or something like that. So that you can do a little bit of this planning.
Yeah. So this is something I skipped over. We looked at that for basically, I think, you know, we had like a library of N, so 6, 8, or 9 rocks that we keep. So if we get a new one, we replace it, but we kind of keep a buffer of rocks that we think are going to be good. And then if we don't get one, I think we refill the whole buffer or something. And you know, like, it's sort of like the trends are as you would expect. So if I have a bigger buffer, then, you know, the rock is, while slightly better. but it's just like we haven't really found like the one thing that just really makes everything much better. Like all these little tricks that we tried, they're incremental improvements, but I don't think this is, I don't think just going with the buffer to 100 would solve this problem. And maybe if we, like so this is, if I only used, let me explain this plot. So this is we used the shape distribution and turned up the noise and said that that we're trying to build these walls with more and more irregular rocks that become sort of less and less look like bricks. The quality we measured destructively by basically simulating shaking to see how much we can shake until something falls off, where like a big fraction falls off or the whole thing collapses. And then the cyan line here is using only the heuristics. When we got a bunch of heuristics from rock stacking manuals, we just looked through and it says like, pick sort of flat things, overlap them, don't do this, don't do that. That are, you can sort of interpret them and turn them into like heuristic evaluations, but it's not, like some of them are kind of hard, right? They kind of suggest that you build a lot of rock walls and this is what you look for. So that was our first try. Then we tried to figure out, this is the Q learning paper. We tried to figure out if we do some reinforcement learning, if we let the algorithm to pick from a larger and larger pool as opposed to one, sort of its action space where it needs to pick both the object and where it places it. If we increase that pool size, does that increase the capability of this reinforcement learner to build better rock walls? Where we try to use, because everything, all the heuristic methods we came up with were like we try to throw deep learning at it, and it's better than our purely heuristic method. But I think once things become pretty irregular, the quality decreases. I don't know if I have that plot here, but we certainly tried to have a variable size of like the pool that we look at. And then we use the heuristic functions on all of them, and we take the best one. It ended up, if it's like after a few, you get slightly better performance, but it doesn't really fix the problem that you can't build very good walls.
Thank you, Nils.
Yeah,
I don't want to use all of your time, so.
No, sorry, thank you. That's a very good question. I mean, I wish I had more satisfying answers to these questions.
But very cool.
Do you mind answering real quick? There was the wall that you have in the slide of the 3 primary concepts. This wall. Is that the same wall from the 2018 paper, or is this constructed in a different way?
This one. So I'm looking at the background stuff. I don't think this is a one from the paper, mostly based on, it is a different experimental setup in the background. So we had a bunch of like undergraduates also build rock walls. This might be a hand-built one, just because it looks like this is in the lab where we got all the rocks from the geology department.
Okay. So this is like a challenging size distribution of rocks, I guess. It's
a challenging size distribution, and I think I don't know if you can still see my pointer. Sort of this is something like sort of the sideways going into a gap is I think something that the heuristic functions wouldn't pick. It might be something that the Q learning thing would have figured out, but based on like the type of walls that are described in the heuristic functions, I think this would be a pretty unlikely placement. It's a good question.
Thank you.
Yep, thank you. I don't have my meeting. I have like another half hour. If anybody wants to stay on afterwards, I'm happy to answer more questions. Otherwise, I don't want to take everybody's time.
Thank you. I think that's a good idea because so let's finish the presentation here. Let's also finish the recording here.
Okay.
And the channel is open. Whoever wants to stay on is welcome to do so.
Yeah. And if you have any questions about this, you can also email me. I'm happy